In this video, we build the starting structure for the transition state optimization for intermolecular protonation involving the central carbon atoms. This demo will also show you some Gauss view tricks which are often quite useful. Our goal is a structure with 3 carbon and 5 hydrogen atoms all in the same plane. We begin by building a 3 carbon chain using the tetrahedral carbon fragment. The resulting chain is close to the structure we want, but some of the hydrogen atoms are mispositioned. Our strategy is to delete the wrongly placed hydrogen atoms and then add necessary hydrogen atoms in the locations where we want them. We delete the hydrogen atoms that are not in the plane of the carbon atoms. Then, change both carbon-carbon bonds to double bonds. At this point, you might be tempted to clean the structure. However, you should not do so. If you do, the entire structure will become linear, as we illustrate here. This is not the structure we want, so we undo the clean operation. We complete the C3H5 fragment by adding a hydrogen atom to each carbon atom. These will be placed into the CCC plane as we want.
The next step is to duplicate this fragment and add a second instance of it to the molecular structure. Select all of the atoms by clicking the Select All button and then clicking in the View window.
Reorient the second fragment and move it into position to bond it with the original one. We allow the 2 hydrogen atoms to overlap in space. Then, delete one of the hydrogen atoms. It doesn't matter which one, and then create a new bond to the second carbon atom. Now, modify the structure so that there is a 90-degree angle between the 2 allyne groups. We accomplish this by modifying the indicated dihedral angle. Next, twist one of the CH2 groups so that it is out of the plane. Do this by modifying the HCCH dihedral angle, setting it to about -144 degrees. The resulting structure has the basic form of the target molecule, but it is not perfect. We refine it using the point group symmetry feature, imposing S4 symmetry on the molecule. Notice that Gauss view tells us that it is possible for this molecule to attain even higher symmetry, but we don't want that right now. Rather, we constrain the molecule to S4 symmetry and enable ongoing symmetry tracking. The last step is to change the hydrogen atoms to methyl groups. With the S4 point group imposed on the molecule, this takes only 2 steps. We check the point group after each addition, reapplying S4 symmetry if necessary. This completes the build process for the starting structure for our transition state optimization.